Might as well become.
That was like 2 years ago.
Okay, so let's start. Near the end of class, we're going to be using two things. One are the handouts that are in the back of the room. If you haven't picked them up yet, just get them during the break. And then we're also going to be using calipers. If you don't have yours, for example, I assume that's what that
I was so
facial
focused on getting
expression
here on
means.
time, Kate. I just
I would
spaced
rather
the
you got
calipers.
here on time because lucky for you, I've got extras.
There we go.
Okay?
All right.
So just, again, it'll be in the second half of class. So at some point, make sure you have your handouts and only if needed, pick up calipers or get out your own calipers. So first of all, are there any questions about the format of the class? Did everybody figure out the weekly to-do list and all that stuff? Any questions at all? Okay, so what we're going to do is we're going to just finish up last week's lecture on cardiac ANP pretty quickly by going through the cardiac conduction system. And good morning. You didn't miss anything. And then we're going to jump into the next lecture. So I'm just going to start back a few slides from where we ended last week. We'll just kind of go blitzing through where the repeat is. So Spencer, what is the starting point for the impulse that travels through the heart?
The SA node.
Excellent, okay. And if you remember the SA node, the location is in the upper right, not really corner, I guess, region of the right atria. Riley, do you remember what SA stands for?
Cytoatrial node.
Excellent, okay. And the SA node is the main pacemaker of the heart, meaning that in a healthy heart, normally the action potential, the impulse, the wave of depolarization that moves through the heart originates in the SA node. At rest, COA, in the body, the SA node has an intrinsic rate of self-excitation. Do you remember?
60 to 100.
Yeah, 60 to 100, okay. And just so we're on the same page, Andrew, what does that mean, self-excitation? What's that all about?
Homeostasis, just,
No, I mean,
like,
that's,
itself, like it excites itself, I don't know how to,
so, but what does that mean? How is,
it doesn't need any external factors to
okay,
it for it.
okay. So what's the connection between pacemaker, Grace, what's the connection between pacemaker and self-excitation? There's a strong connection between those two words. What are we talking about?
Can I phone a friend?
Excuse me?
Can I phone a friend?
Yes, you can phone Natalie.
Sorry, no, you're good. So I was talking about like the SA node acts as a pacemaker, and that's what's propagating the signal to the rest
Yes,
of the heart.
yes. I know that's exactly what Grace meant to say.
Yeah.
So, remember that generally most of the cells in the heart are depolarized. They depolarize because they receive a little bump, a little action potential from the neighboring cell, and then they pass it on to the next one. So that's not self-excitation, and by excitation we essentially mean depolarization, right? That's created by this impulse moving through the cells, okay? When we talk about pacemaker cells, they have a quality of self-excitation, which means just sitting around, they will all of a sudden just throw out an electrical impulse, okay? And that's what the pacemaker cells do. The SA node, which is a fairly complicated little structure, contains a number of pacemaker cells, and when we say it's the main pacemaker of the heart, that's the originator of the electrical impulse. So that's what we mean by self-excitation. Does that make sense? Okay. Okay, picture of the SA node, which is all of this here. Now, we had this slide last week, but it was right near the end, and I figured everybody was tired. And it's a pretty important explanatory note. So if you think about it, we've already said that the way electricity travels through the heart and the cells depolarize, which leads to mechanical contraction, electrical depolarization leads to mechanical contraction, is that the cells sort of push the electricity, they bump the next one, which bumps the next one, and so forth. Now, I think I'll draw a picture here, is we know that the SA node is the main pacemaker of the heart. And Anne, remind us, where is the location of the SA node?
Up in the top upper right corners of the right atrium.
Perfect, okay. So if here's our very perfectly drawn heart, in case you don't recognize it, atrium, atrium, ventricle, ventricle. The SA node is here, okay? Now we know that's where the electricity originates. So if you think about it, okay, that seems really straightforward. The electricity, originates here, and the cells will depolarize each other. So if there was nothing else within the heart other than a blob of cells, you could see that the electricity would just kind of move through the heart like this, and then it would move through the heart like this because it's all originating from here. So in other words, if there was no other structure that was significant, the right atria by definition would depolarize before the left atria because it's closer to the SA node, right? And the top of the ventricles would depolarize before the bottom of the ventricles because they're closer to the SA node, right? And we know that depolarization leads to contraction, so we've got a problem here. Because who knows, does the right atria depolarize and contract before the left atrium? And how do they do it? How do they depolarize relative to each other?
There's the Bachman bundle goes over to the left side.
Excellent. But, excellent. What I'm fishing for is the idea that the right and the left atria depolarize simultaneously. And as far as the ventricles go, it's a really complicated picture of depolarization and a really complicated picture of contraction, which basically, simplifying it, says that the bottom goes first. But wait a minute, the bottom is further from the SA node. Okay, so I'm introducing the reason why we have this speedy conduction system, why we have these tracks of very rapid depolarization that sort of thread their way through the myocardium. So the speedy conduction system is so much faster than the normal cell-to-cell conduction that what it allows the heart to do is to essentially, this is just an analogy, throw electricity to various parts of the heart so that the conduction system will orchestrate the pattern of depolarization. And as Kyle just mentioned, one of the first things that happen is we know we have these specialized system of conducting system, these specialized tracks that run through the atria, and one of them, which is called the Bachman's bundle, goes over to the left atria. So how is it that the right atria, in actual fact, the right atria will depolarize just the fraction of a second before the left atria, but it's virtually the same, just a tiny bit before. How does that work? Well, this specialized tract of conducting system takes the impulse and it flies over here so that the left atrium is able to depolarize. The left atrium will depolarize similarly to the right atrium. We also know that the conduction system is going to fly down the septum of the heart to deliver electricity to the bottom of the ventricles very quickly, and that's going to allow this very complicated pattern of depolarization and contraction. So this slide, what you're going to see here is this concept. If you can get this concept, it'll really help you. That's the conduction system, really fast, okay? And then the rest of the electricity, it's like we have this depolarized band that almost depolarizes so quick it's almost simultaneous. We're talking fractions of seconds, which allows this whole area to spread out in a very particular way. Okay. Does that make sense to people? Okay. So, impulse leaves the SA node and speeds through the conduction system where there's specialized tracks. Those are the green parts. It then spreads out through the atrial myocardium. Again, here's the Bachmann's bundle that goes over to the left atrium. Here's a a simplified version of the conduction system. We have the internodal pathways that go down to the AV node. Okay. Now, there are some, Cody, there's some special qualities of the AV node. What are they? What makes the AV node kind of its own little thing, its special thing?
It delays the shock just a second.
Excellent. It slows down the impulse. Okay. That's one thing. What else can anybody tell me about? What's special about the AV node? There's a pause. So the other things, and this is really important that you know this, it's the only way for the impulse to get from the atria to the ventricles. Everything else, let's go back and look at our picture. Everything, like you would think, well, how come it just can't come straight down here? Why can't the electricity just go straight down from atria to ventricles? Why does it have to come through here? And that's because the atria and the ventricles are separated by this this non-conductive tissue. And so there's no way that electricity can get from the atria to the ventricles except, in a healthy heart, except going through the AV node. And then what happens is the electricity comes down, it gets to the AV node, and as Cody mentioned, it pauses. So Chris, what's the significance of that pause? Who knows? Yes,
So it allows the ventricles to fill.
well, yeah, it allows time for the atria to contract and the ventricles to fill. So it's just pausing for a moment to allow everything to sort of catch up with itself. Okay. Now, the other thing, so this is pretty straightforward. This is pretty straightforward. This, I don't think we're going to understand for a while. I'll explain it, but if you're thinking, well, who cares about that? You'll see when we get to arrhythmias like atrial fib. Anybody heard of AFib, atrial fibrillation? Yeah. So basically, not only is there a pause in the AV node, but there's a cap on the speed. It can only travel so fast. The impulse can only, so many impulses per minute can go through the atria, okay? And so when you have something like AFib, where you have, and again, we'll talk about this in a few weeks in detail, but essentially you have electrical chaos in the atria and many impulses want to get down to the ventricles, the AV node will limit the rate of transmission, okay? And don't worry too much about that for now. We'll get back and explain that better when we get to AFib. Okay, we're just going to go through these a little bit. The only pathway, so non-conductive connective tissue separates the atria from the ventricles. In the healthy heart, the AV node is the only conductive tissue, okay? The all-important pause. The AV node delays impulses by about 0.09 seconds, which, what's the big deal with that? But in cardiac time, that's an age, Okay, that's a long time. By the way, don't memorize 0.09. So that I want you, it's really important you have the concept of pause, but you don't have to know exactly how long it is. So, as we've said, this ensures that the atria have ejected their blood into the ventricles before the ventricles contract. A little bit more, and that limits the rate of transmission. So generally in an adult heart, the upper range of transmission through the AV node is about 220 beats per minute. So what that means is that even if things are happening more quickly in the atria, what gets down to the ventricles can't be above that, okay? And again, we'll come back and talk about that more when we get to the specific arrhythmias. Okay, so we get to the AV node, and then we jump off into the ventricles, and we get to what's called the bundle of His, right below the AV node, and it immediately bifurcates, the conduction system immediately bifurcates into the left bundle branch, which goes into the left ventricles, and the right bundle branch, which goes into the right ventricle. Then the bundle branches start bifurcating into these very small, they're kind of like capillaries, except they're not blood vessels. But again, it's sort of, it goes from large to small, the way that blood vessels will go into capillaries. And they infiltrate the myocardium. Again, the purpose of the Purkinje fibers, the purpose of the conduction system is to deliver electricity extremely quickly to all parts of the heart. There's just a better picture, the bundle of His. So the bundle branches are the bifurcation of the bundle of His. Okay. Purkinje fibers, the bundle branches divide again into the extensive system of Purkinje fibers. And then this allows the ventricular myocytes to depolarize and contract. So again, this is something you need to know, okay? If I were to put this diagram on a test, you should absolutely be able to label it, okay? You should know the SA node, the AV node, you should just know this, because this will help you. Okay, here's just a picture of here's the endocardium, and the Purkinje fibers are on the inside. So what happens is the electricity travels on the inside near the endocardium, and then it travels to the outside of the myocardium. So just a computerized version showing the Purkinje fibers. Okay, this looks like we're talking about blood. We're not. We're talking about electrical depolarization. So number one, there's a start. The SA node depolarizes, throws electricity out into the atria. The electricity spreads out through the atria, allowing the right and left atria to depolarize nearly simultaneously. Then the electricity goes through the AV node, down through the conduction system, delivering electricity to all parts of the ventricles, and the ventricles will start to depolarize, followed by contraction near the bottom, okay? And it moves up toward the top, and then we start over again. So briefly, the SA node and all the conduction system are at rest. The SA node initiates the action potential. You can see that there. The atria depolarize almost simultaneously from top to bottom. Okay. Meanwhile, the impulse has reached the AV node, because remember the conduction system is so quick, and we have to have a pause because we have to give the atria time to depolarize and contract. Okay. Following the delay, the impulse travels through the bundle of His and the bundle branches, reaching the apex of the ventricles, and then the impulse spreads to the contractile fibers of the ventricles. Ventricular contraction begins, okay? Okay. And then the absolute numbers are meaningless in this class, but I just want to give you a sense of how quickly things are traveling. So if we look at within the muscle itself, that's off of the conduction system, it's 0.5 meters per second. And then the AV node, you can see how it slows down there. And then, so when we look at where it says ventricular muscle and atrial muscle, this is off, not on the conduction system. The muscle cells themselves are, the impulse is still traveling through the muscle, but you can see how much faster it is on the conduction system. So you can see the bundle of His is 2 meters per second, left and right bundle branches 2 meters per second, and then the very fastest are the Purkinje fibers, 4 meters per second. But the muscle cells themselves off of the conduction system are 0.5 meters per second. So, a quarter to an eighth as fast. Now, okay, we've already said this multiple times, so I'll just kind of blow through these slides. Conduction system, rapidly transmit the impulse to strategic points of the heart. Okay, so the left and right atria can contract simultaneously. So all parts of the heart act in specific, reproducible, and efficient manner. Now, damage to the system. The reason we're spending so much time on this part of the heart is when we talk about different dysrhythmias, different arrhythmias, which is what ECG class is all about, are different dysrhythmias and how they appear on the ECG. Many of them are caused because of damage to the conduction system. Now, one final note. You're going to hear this term, which I believe is quite misleading, okay? But it's used all the time, and we will use it. You're going to hear this term cell-to-cell conduction. If you hear the term, the electricity traveled through the ventricles with cell-to-cell conduction, that specifically means that it's traveling through the ventricles off of the conduction system. Cell-to-cell conduction means it's myocyte to myocyte, okay? It's misleading because the conduction system also is made up of cell-to-cell, so the traveling within the conduction system actually is one form of cell-to-cell conduction. But just by convention, when we talk about cell-to-cell conduction, this means the relatively slow conduction between myocytes and not the speedy conduction system. Okay, here's just... nothing really significant here, just kind of a... Okay. Now, we said that all of this occurs because of the SA node. What happens if the SA node stops working? Is that it? Okay, why not, Andrew?
The other cells kind of act as a backup.
Yeah, exactly. Okay. So actually, all of the cells within the conduction system possess automaticity. Now, I'm pretty sure automaticity was in your reading, so who remembers what that means? We've actually already used the term, but a different version. What's automaticity? Yeah.
Is it the ability to self-excite?
Yes, that's exactly what it is. When we talked about self-excitation, another term for that is automaticity. Now, all of the cells within the conduction system have some form of automaticity. So they can become pacemakers ready to act as backups if the SA node fails. Okay? Okay. But that kind of begs the question, we're looking for this efficient, coordinated system where the SA node is in charge of the heart. Why don't these backup pacemakers try to take over the heart? If every part of the conduction system has the ability to become a pacemaker itself, why don't we have anarchy in the heart where all these pacemakers are trying to take over? How does the SA node maintain control? Yeah.
Is it because it's kind of regulating the whole propagation? So if they're all depolarizing at relatively the same time, but they have to take the same time to repolarize?
You're almost there. So the SA node is in charge, But one of the backup pacemakers is the AV node, okay? Because that's part of the conduction system. That's an important pacemaker. In fact, many times if the SA node fails, the AV node takes over and becomes the pacemaker. But what's to prevent, probably all of us are sitting here and our SA nodes are controlling the heart. How come our AV nodes aren't saying, wait a minute, I want a piece of the action. I'm a pacemaker, I can do it too. How does the SA node keep it in control?
Every time the cells downstream depolarize, they have to restart their cycle, and they
Yes.
all depolarize, or their automaticity is slower than the
Bingo.
SA node.
That's it, okay. So we'll go through that. Why don't the other pacemakers take over? Okay, so that being the AV node, what's to keep the AV node from taking over? Well, the intrinsic rate of the pacemakers, so Chris, we've already said what the SA node is. What was the intrinsic rate? Do you remember that? It was 60 to 100, excellent. And Kyle, do you remember from your reading perhaps what the AV node is?
I think it's 40 to 60.
Excellent. Anybody remember what the Purkinje system, what its intrinsic rate of automaticity is?
Less than
Yes, perfect, less than 40. Okay, so there's something called overdrive suppression, and this is how it works. And it's exactly what Kyle said, okay? Let's suppose that if you think for a minute about a pacemaker within the AV node, it has an intrinsic rate of 40 to 60. And what that means is if the SA node goes away, the AV node has been waiting and waiting. It's getting closer and closer and closer to throwing out an impulse. And if the SA node's not there, it will start doing it, okay? But the SA node is faster. The intrinsic rate is faster than the AV node. So if the SA node is working before the AV node has a chance to depolarize on its own and throw out its own impulses, it gets depolarized from above, okay? So that's why as you move down the heart, because what we want is the closest thing toward normal, and the closest thing toward normal is up in the SA node. So as you move down the heart, the rate of pacemakers, the intrinsic rate will get slower and slower. Okay, so that's the end of that lecture. So let me quick change the recording, and yes.
Just for a second, would you want to go back to the
Sure,
intrinsic
absolutely.
rate? Sorry.
So back to the previous slide?
Yeah, the numbers.
Okay. Oh, that one. Oops. Come on, wait a minute. Okay, here we go. A lot of times with a Purkinje system, you'll see 20 to 40. A lot of references will say 20 to 40, and that's fine, but it can actually go slower. So if you're asked what the rate is, 20 to 40 is a perfectly good answer. I think less than 40 is a little more accurate.
Thank you.
Okay. So let me just change this.